Hello, everyone. Today, I would like to present to you something that is very close to our hearts, especially because it's week 12, which is exactly dying. So specifically, I would like to talk about using non-homogeneous Markov chains to calculate when we're expected to die. So a little bit of a disclaimer, these results are not rigorous because I'm lazy. So I tried to look for resources with textbooks and papers, but it wasn't very helpful. Why is it not moving? Hello? Okay. So this may disappoint people who like rigor, but I'm perfectly fine with it. And if you're not, then I will coerce you to be fine with it. The other thing is that I'm actually not dying. This is definitely not an evil clone. Anyways, let's start with what a non-homogeneous Markov chain is. So basically, it's a Markov chain that depends on time, but not the past. You can think of it like a time continuous Markov chain, but you can't shift it around. So for example, the probability that you go to state J, given that you start at state T, is not going to be the same as going from I to J in state 1 and in state 0 to 1, which is the second probability. And the top one means that you can completely ignore everything before the current state, and then the probability would still be the same. Also, I would like to note that the model shown here, the one that I used, is discrete time. So the next thing is modeling a stochastic process using non-homogeneous Markov chains. Definition-wise, it is quite similar to homogeneous ones, but the main difference is that instead of having one P matrix or one transition matrix, we have instead a sequence of P matrices where T denotes the time. And you can think of PT as a storage of the transition probabilities. So it still has the same shape. So it still has I and J, and then ij are states in the state space S. So let's start with the simple model, which is the life-death model. So we're going to make a few assumptions. Number one is that you're 20 years old, including Ajahn. 2, you are an average human being in terms of physical health, because we all know that people who take this class are above average in intellect. And the last one is that cancer and deadly diseases hasn't been invented yet. So let me just explain something from a class that I didn't take, which is actuarial math. So we call the ultimate survival model. We define mu as a function of x, and the definition is up on the screen. And then we also define TPX to denote the probability that someone will live for longer than t years, given that another t years, given that they've already lived for x years. And this is computed by the exponent term. And here, x denotes the starting age, which is how old you are when we compute this probability, and t denotes the number of years after x. Now, let's try to model the ultimate survival model with non-homogeneous Markov chains. So we define the state space to be alive and dead. Obviously, dead is a recurrent because you cannot come back to life. And we try to find the transition probability at year t. We also define kqx to be the probability that you will live until t years, but not after it. So it's kind of like the probability that you will die in t years after living for x years. And we also define the transition matrix, PT, to be, so this one is basically probability that you stay alive. This is probability that you die, and then if you die, then it comes back to itself. Wow, I stole it from Ajahn. So when we're computing the expected time left to live, we have to end up using the usual way of computing it instead of the time, because the reason for this is because the probability is time-based, and we're trying to find the expected number of years, so we use that method instead. And the results come out to be that you're expected to die at around age 86, which is great, maybe. And you may be wondering, where is the system of equations? Some of you may have already been spoiled, but anyways, let's try using first step analysis to find the expected time left to live. So the problem here is that because the expected hitting time, which is expected time left to live, is time dependent, so we'll end up with infinitely many equations of that form, and I don't know how to solve that, so we're just gonna throw that in the bin and use the usual one instead. And that concludes my presentation for the first half of my project, because we have a more general model. So now we define one more stage by basically inventing cancer. So the sequence of transition matrix can now be defined as this. So this is basically probability that you'll stay healthy. This is probability of getting cancer at year T. This is dying. This is dying given that you're healthy. This is dying given you have cancer. And this is staying alive, but you still have cancer given that you have cancer. And then this one is dying from cancer. And then the last one is dying in general. Also, I would like to note that there's no like fancy survival analysis used for this one because I'm too lazy to find it. So we're just going to use simple regression. So first, we have to find the rate of getting cancer. It's fitted with... Where is my picture? Okay. So it's fitted with this function. I got that from ChatGPT, but I simplified it a little bit. And the data that I took is from the SER program from the National Institute of Health. So it's based off only Americans, which is probably not the most representative of us here. But it's the only one that I can find, and this is the fit that I got from it. The other one is finding the mortality rate of cancer. This data is from the Institute for Health Metrics and Evaluation. The data that we're using is from year 2014 to 2019. And the function that we fitted it with is a polynomial of degree 4. And you may be thinking that this is not a very good fit, but I asked 8 people and 7 of them said that it's a good fit. So by democracy, it's a good fit. And then let's try to put all the probabilities together. You may notice that this probability looks weird because normally it would look like a curve that comes up and then eventually comes down later. But because I'm trying to use the probability for a simulation, what could happen if it comes down is that past some point, if you have not died yet, then you're basically immortal because the probability of you dying is so long. So it's basically 0 after some point, and then you basically live forever. So I basically made it a non-decreasing function. So if it's come up to some point, then it never dips down below that. And then so that's why it plateaus after like this point, and for the rest as well. And this is the final plot, the plot that we've been looking for. So after running some simulations, the probability of dying or living longer than another T years, this is compared to the probability that we get from the survival model. Okay, so this is what the result that we get. And note that the rate of people dying, or the probability of people dying, drops lower before the ultimate survival model. I have 2 explanations for this. Number one is that because now we are also considering cancer, people are already dying over here. So past this point, then there are less people to die. So the probability of someone dying at a certain age, I found that it's actually computed by, it's more like the probability of someone living for longer. But the thing is, it doesn't take into account how many people are already alive. So less people are already alive at a certain age. That's why the probability drops down, even though you should already be dead at that point. And the second explanation is that the model is bad, which is a likely thing. And the last thing is expected time left to live. So when we're considering cancer, we're expected to live until age 67. I'm not sure if that's a good thing or not, but lesson of the day is that you should not invent cancer. And that concludes my presentation for real this time. Thank you. Any question before I pass out?
What would be at the factor that is missed to cure cancer?
The cure times?
Yeah, missed to cure cancer this.
All right, because wait, let me show. This one. Why is it so slow? But anyways, if it's not gonna show up. Okay, so yeah, I couldn't find any data on curing rate of cancer. That's why the probability of you having cancer and going back to being healthy is 0. But, I know that it's actually not 0, but I couldn't find any data on it. But if it's not 0, then the probability, the model, the final plot should be shifted a little bit to the right. So people should be living longer because you can actually recover from cancer and not like live with it the rest of your life.
So the death rate is the same?
The death rate is, it should be the new model, the death rate is higher because the expected time left to live is lower. So the original model, the ultimate survival, expects you to live until 86. This one only expects you to live until 67. But I feel like there's something to fix with the simulation algorithm. The idea for the algorithm is that you give it a year, and then it simulates the probability that someone lives until that year. But maybe it's not like the best way of simulating it, but I couldn't come up with anything else, so I stuck with it.